एक काम करते हैं, हम लोग इंस्टीट्यूट के बाहर नहीं इनऑर्गेनिक का इंडिविजुअल क्लास लगा लेते हैं।
अच्छा?
हाँ।
क्या होगा उससे? क्या होगा उससे? नहीं होगा क्या? अच्छा ही पढ़ाएंगे ना, वो तो ये भी पढ़ा रहे। मीना प्रॉब्लम टीचर्स में नहीं है, इस सब्जेक्ट में। निहायत ही बोरिंग सब्जेक्ट है यार ये। सिर्फ फैक्ट्स है जिनके कोई लॉजिक्स नहीं है। लॉजिक के नाम पे जितने रूल्स नहीं है उससे ज्यादा तो एक्सेप्शन है। पहले ऑक्टेट रूल में बताएंगे सिर्फ 8 इलेक्ट्रॉन होने चाहिए, पर फिर कितने भी इलेक्ट्रॉन का कंपाउंड बना रहे हैं, 4, 6, 7, 8, 10
और 12।
हाँ, अरे ये लोग है ना एक्सेप्शन बोल बोल के, एक्सेप्शन नहीं है ये, एक्सक्यूज है, एक्सक्यूज, प्योर एक्सक्यूज। इनके पास है ना सारे आंसर देने वाली कोई थ्योरी नहीं है। और थ्योरी होगी भी कैसे? कैसे होगी बताओ? थ्योरी देते थे आइंस्टाइन, न्यूटन जैसे जीनियस लोग, पढ़ते ही नहीं थे। लॉजिक नहीं, यहां है एक्सेप्शन, एक्सेप्शन, एक्सेप्शन।
ऐसी बदनाम कर रखी है इनऑर्गेनिक केमिस्ट्री। जितना रैंटिंग, जितने मीम इनऑर्गेनिक केमिस्ट्री पे बने हैं, उससे ज़्यादा मीम शायद ही किसी सब्जेक्ट पे बने हो, किसी भी सब्जेक्ट में, एज फार एज आई नो। भाई, इनऑर्गेनिक केमिस्ट्री से प्यारा सब्जेक्ट कोई है नहीं. It is a do or die subject. If you know the answer, you will get the marks just like this. And if you do not know, no matter how much you try, there's no enlightenment that is going to happen on the spot. So you can either score it in 30 seconds or not. That's how easy your inorganic chemistry is. अब आप मुझे एक बात बताइए, अगर 118 elements हैं, what is your expectation? Your expectation is all the 118 elements should have the same nature, huh? Tell me one thing, if there are 10 students studying for JEE in one classroom, okay, all of them are studying in the same coaching, all of them are of the same age group, are they going to have the same nature? Hey, come on, they're not going to have the same nature. How can you expect 118 elements to have the same nature? And then you're expecting there should not be exception. You are not going to have the same nature as your brother itself, your sister itself. You have a different nature as compared to your parents also. If 4 members of a family can't have the same nature, how can you expect 118 elements to have the same nature? Tell me one thing. It is not a Newtonian, science wherein things are macroscopic. It is not simple action and reaction. It is not simply that, okay, I got a jerk because my vehicle was moving in a bus. So, okay, there is some inertia and there is inertia of motion, inertia of rest. Okay, it's not a macroscopic body. Come on, we are talking about microscopic elements, my dear. To know microscopic elements is a task. To know microscopic elements is an art. To know microscopic elements is deep, deep science, which we call as chemistry. Nonetheless, the subject is never bad. Always remember, it is your approach to the subject that might be bad. So have a positive approach towards any subject that you're studying, and studying from a better teacher, good teacher, is always something that will make your approach best, right? So this is me, Nitika, and I am going to start with a very, very important session today, which will help you with a lot of questions. Like, what kind of questions? Questions related to, number 1, how many peroxy linkages there might be, or whether there is going to be a peroxy linkage or not. If not a peroxy linkage, then whether an oxy bond is possible, or is there an element-element linkage or a metal-metal bond, okay? All of these, and then whether oxygen is present as an oxide or is it present as a peroxide. Where is oxygen in -1 oxidation state? Where is oxygen in -2 oxidation state? How many peroxy linkages are possible? How many oxy bonds are possible? And 100% there are going to be at least 2 questions from today's session. So without any further ado, let's get started. Okay, so overall there can be 3 possibilities. Case number 1, there is going to be a calculated oxidation state greater than the maximum oxidation state. Case number 2, calculated oxidation state might be equal to the maximum oxidation state. Case number 3, calculated oxidation state is less than the maximum oxidation state. How do you know that calculated oxidation state is greater than maximum? Simply by assuming that oxygen is present in the oxide form. Oxide means O2 minus. But there might be a case when oxygen is not -2 but rather -1. But for our finding the oxidation state purposes, we are going to consider oxides. Okay, but might be the case, why is the original oxidation state going to be different? Because the oxygen that you thought was oxide is rather a peroxide. Okay, so let's get started with different examples and understand it deeply. Questions will help us understand the topic well. First one coming your way. Check this out. So let's start with the case number 1, where the calculated oxidation state is greater than the maximum oxidation state. So let's start with H2SO5, peroxy monosulfuric acid. The calculated oxidation state, I'm assuming that you know how to find out the oxidation states. If not, let me know in the comments if you're not clear with how to find out the oxidation states, okay? That's a prerequisite. Before this session, you need to know how to find out the oxidation states. Okay? Cool. So H2SO5 plus 2 plus X minus 10 is equal to 0. So your X is going to be equal to, can I say 8 plus 8? Whereas we should already know that number of electrons in the valence shell are the maximum, will give you the maximum oxidation state, right? Which is plus 6 for sulfur. So calculated oxidation state minus maximum oxidation state divided by 2/1 will give you the number of peroxy linkages. Now when your central atoms are 1, so how many central atoms are there? There is just one central atom. Then you have to divide by 2. If the central atoms are more than, if equal to or more than 2, okay? If the central atoms are greater than or equal to 2, in such a case, make sure what you're supposed to do, you are supposed to divide by 1. That's something that you have to keep in mind and your life will be sorted. Super sorted. Okay, so calculated oxidation state minus maximum oxidation state, when you do, what you get? 8 minus 6 by 2, that means 1 peroxy linkage is present. So in such a case, your calculated oxidation state is going to be greater than maximum, and what will be the actual oxidation state henceforth? Your actual oxidation state is going to be the maximum oxidation state only. Okay, how? Let's figure it out from the structure itself. This is how your per-sulfuric acid or peroxy monosulfuric acid would look like. You know that your sulfuric acid looks like this, OH and OH like this. So the number of bonds sulfur is capable of forming is 6 here. Double bonded oxygens are 2. Instead of just one OH, it has OOH. That's the only difference. So keep that in mind, and one OH remains as it is. So that's the difference between the two. So if you observe now how to find out the oxidation state of the central atom here. So these oxygens, doubly bonded oxygens, are -2 and -2. This is -1 because it's OH, and this is also -1. So +6 becomes the oxidation state of the central atom. So always make sure you keep checking with the structure also what's the oxidation state that you're getting, actual oxidation state. All right. But when we are finding out, when we are doing the calculated oxidation state, you can always find out using the concept that oxide is present, O2 minus. Next one, for example, you have CrO5, the OgCrO5. Everybody knows it has butterfly-like structure. But let's say if you do not know, can you know? Of course you can. You're at Rasayan Prayogshala, so you would know. So calculated oxidation state, can I say, is X minus 10 is equal to 0. So X is going to be equal to +10, right? Maximum oxidation state for chromium is +6. You know it is 4s1 3d5. So total 6 electrons in the valence shell. Number of peroxy linkages, can I say 10 minus 6 divided by 2. So why am I dividing it by 2? Because the central atoms, hello. How many central atoms? 1. So you have to divide by 2. Don't forget. So 10 minus 6 by 2, 4 by 2 will give you 2. So there are 2 peroxy linkages. Yep, the wings, the wings. So these are the antennas and this is the wing number 1, wing number 2. So you have butterfly-like structure coming your way. Let's check the actual oxidation state from the structure. So since these are peroxy oxygens, so -1 and this one is -2. So you just do the complementary positive charge on chromium. So the neutrality is always maintained. The nature is so beautiful. Instead of ranting, we should always appreciate nature. So 2, 3, 4, 5, 6 plus 6. Bingo. Chalo. Next one. H2S2O8. Okay. So again, plus 2 plus 2x minus 16 is equal to 0. So 2x is going to be equal to 14. X is equal to 2. That means plus 7. Now, mind you, we have 2 central atoms. So you have to divide by 1 in the formula, calculated oxidation state minus maximum oxidation state divided by 1. So far, if you observed what I have done, because there were only 1 central atoms in our example number 1 and example number 2, we have divided by 2. But now you have 2 central atoms. So you have to divide by 1 now. So maximum oxidation state for sulfur you already know. So calculated minus maximum divided by 1. Be mindful. If you are able to decode this, you're sorted, not for NEET, not for JEE, not for JEE Advanced, but for life. So, number of peroxy linkages are going to be 1 only, and this is how your structure is going to look like. So, there is just 1 peroxy linkage which is right there in the center. Cool? Now, the next one, H4P2O8. Very interesting. This is game. This is fun. I love it. So, plus 4 plus 2x minus 16 is 0. 2x is equal to your 12. So, x is going to be equal to plus 6. Maximum oxidation state for phosphorus is plus 5. That's right. How many central atoms? There are 2. So, what do you have to divide by? You have to divide by 1. So, do not forget the rules. The more you practice, the more pro you become at. Okay. So, 6 minus 5 by 1, that means 1 peroxy linkage. So, the questions related to peroxy linkages can be solved. The questions related to the actual oxidation state. So, in this case also, what shall be the actual oxidation state? It is going to be the maximum oxidation state only, plus 5. Let's check with the structure. So, when you have 2 central atoms, you can think of it that the peroxy linkage has to be within the 2 central atoms, like this. And then you have how many hydrogens? So, must be like this. 4 hydrogens must be like this. So, 1 peroxy linkage. Let's check individual phosphorus. Minus 1, minus 1, minus 2, minus 1. So, 2, 3, 4, 5 plus 5. Hello. The same control C, control V for the other one, plus 5. So, the actual oxidation state for H4P2O8 will be plus 5. Yeah. Moving on. K3CrO8. OG. Very, very cool. What do you have? Calculated oxidation state is going to be plus 3 plus X minus 16 is equal to 0. So, X is going to be equal to 16 minus 3, 13. Oh. What is the maximum oxidation state for chromium? We already know plus 6. Now, in this case, mind you, we have the central atom equal to 1. So, you're supposed to divide by 2, right? But that means number of peroxy linkages will come out to be a fraction. 13 minus 6 divided by 2. So, in such case, always add 1 in the numerator when you have a scenario where a fraction is coming. If fraction is coming, add plus 1 in the numerator, and this plus 1 adding is an indication that the calculated oxidation state, of course, is greater than maximum, but the actual oxidation state is not going to be equal to maximum, but 1 less than maximum. We'll check. So, here 13 minus 6 plus 1 divided by 2. So that makes it 14 minus 6. That means 14 minus 6, 6, 7, 8, 9, 10, 11, 12, 13, 14, 8 by 2, 4. Oh, that's quite many. 4 peroxy linkages. Let's see how can we adjust 4 peroxy linkages. Do you see there are 3 potassiums? So at least 3 peroxy linkages can be in the form of OO minus like this, which can be taken care of. Like I said, the molecule is supposed to be electrically neutral. So the 3 peroxy linkages are taken care of like this by the 3 potassiums. According to the formula, the number of peroxy linkages should be 4. 3 are sorted. What about the 4th one? See, 4th one you have to put in such a way that it is not swaying in the air. हवा में उड़ता जाए मेरा लाल दुपट्टा मलमल का. No हवा में उड़ता जाए, okay? For my English speaking crowd, please, you do not have to make the peroxy linkage fly. You have to give it some support. Give it support with the chromium itself, and this is how it is going to look like. Isn't it? So yeah, K3CrO8 looks like this. Now let's move on to, before we move on, check -1, -1, -1, -1, -1. So the oxidation state of chromium, the central atom, is +5, and that's what I said. Your fractional number of peroxy linkages is an indication that the actual oxidation state is not going to be equal to the maximum oxidation state. Be mindful. If needed, watch the video again. And I'm telling you once again, this is a Rambaan video for you. Save it. The more number of times you will practice, better you will become at it. So let it be in your saved list. Moving on. Case number 2. H2S2O7. Oleum, it is called a disulfuric acid. So what do? Find out the calculated oxidation state. +2 plus 2x minus 14 is equal to 0. So 2 plus, or I can just solve the numbers right away. So 2x is going to be equal to 12. Right? So x is going to be equal to 6. And the calculated oxidation state is turning out to be same as the maximum oxidation state. How to find out the number of peroxy linkages is a different formula. How to find out oxy bonds, there is no formula, mind you. In such cases, you have to, there's no formula. Keep that in mind. Do not apply the formula that we have done for number of peroxy linkages to find out the number of oxy bonds. Whenever calculated is turning out to be equal to maximum, make sure you take care of the structure on your own. So H2S2O7. So there is SOS, save our soul. H are 2. So this is how your molecule is going to look like. All that you can be vigilant about is when you have more than 2 central atoms. Okay. So like for example, here also you have 2 central atoms. More than 2, you can be a little vigilant. If there is a common factor, then that means the oxy compound that we have is going to be cyclic. I'll show you with the example, but for now, let's do this question. H4P2O7. So +4 plus 2x minus, so there are 7 oxygens. So 7 into 2, 14. So 14 minus 14 is equal to 0. So 2x is going to be equal to 10. So x is going to be equal to +5. And hey, that's what is the maximum oxidation state. So calculated is equal to maximum. That means MOM bond, or there is going to be POP bond here. How many? That the formula cannot tell. We have to draw and find out. So POP, this is how I'm going to draw 4 oxygens, 4 hydrogens and 7 oxygens, out of which 3 oxygens I've already taken care of, if you see. So now what do we have? 4 hydrogens which are going to be with the oxygens like this. So 1 POP bond here, right? Next one. K2Cr2O7. Again, plus 2 plus 2x minus 14 is 0. So 2x is going to be equal to 12. So x is going to be equal to plus 6, and that's what is the maximum oxidation state. So number of oxy bonds, again, no formula. All you need to do is draw it. So CrOCr, and then there are going to be oxygens. How many? 7 oxygens. So this is what we have. So O minus, we have 2 potassiums that can be taken care of by O minus. So 1, 2, 3, 4, 5, 6, 7. 7 oxygens are right in front of you. 2 potassiums are right in front of you. Mind you, this is very famous example wherein the configuration is also asked. The hybridization is also asked. So chromium has a hybridization of D3S here, very OG, very famous. But sp3 hybridized oxygen is present. So this also you should be aware of. And yes, number of CrOCr bonds are going to be 1. There you go. So these are the examples wherein just 2 central atoms are present, right? What if now you have something like this, P4O10? Do you understand how many central atoms are there? 4. Is there a common factor? Yup. How many? 2. 2 is a common factor. This is an indication that this can be a cyclo compound. Always be mindful of this. So calculated oxidation state is going to be equal to 4x minus 20 is equal to 0. So x is going to be equal to 20 by 4. That means plus 5. And maximum is also plus 5. So there are going to be POP bonds. And when I draw POP bonds, this is how the POP bonds are going to look like. 1, 2, 3, 4. 4 phosphorus I have taken care of. Check and drawn the POP bonds. And now every phosphorus will have a doubly bonded oxygen like this. So how many oxygens have been taken care of? 8. 2 are left. So that can be taken care of by the cross POP bonds like this. So total POP bonds are 6 POP bonds. Very, very important question. So if this question pops up, 6 POP bond, you're not going to do it wrong. You're my students, my lions. Yeah? All right, next one now. Keep in mind, what if the calculated oxidation state comes out to be less than the maximum oxidation state? So when it was greater, we had a peroxy bond. When it was equal, we had an oxy bond. When less, we will have a element-element bond. I'm writing it as MM bond, element-element bond. Let's try it with an example. You have a dithionic acid. So plus 2 plus 2x minus 12 is equal to 0. So 2x is going to be equal to 10. That means x is going to be equal to plus 5. But, hello, the maximum oxidation state for sulfur is plus 6. We have been doing now this thing from time immemorial. So, calculated minus maximum by 2, nothing like that. The moment you have the calculated oxidation state less than the maximum oxidation state, yes, your actual oxidation state is going to be equal to whatever you have calculated. So, case number 1, when calculated was greater than maximum, you have to be careful. The general scenario is the calculated oxidation state is never going to be equal to the actual oxidation state. Always in case number 1, the oxidation state actual will be either equal to the maximum oxidation state or maximum minus 1, like the case I showed you. Then case number 2, the calculated oxidation state will be equal to the maximum, will be equal to the actual oxidation state. Case number 3, the calculated oxidation state will be equal to our actual oxidation state. Now, structure is most important for us. So, S bond is going to be there. 6 oxygens, 2 hydrogens. Always hydrogens are going to be attached to oxygen like this. So, this is how your dithionic acid looks like. Check this out. 1 element-element bond, SS bond. Next one, H4P2O6. So, 4 plus 2x minus 12 is equal to 0. So 2x is equal to 8. So x is equal to plus 4 And maximum oxidation state, now you know that is +5 for phosphorus. So calculated oxidation state is less than maximum oxidation state. Indication, it is going to have PP bond, PP. So PP bond like this, a doubly bonded oxygen like this, 6 oxygens, 4 hydrogens, make sure you put the hydrogens with oxygens like this, 1 PP bond like this. Easy? Next one, H2S2O3. This is a little tricky, but nothing is tricky with Nitika ma'am, like you know. So, +2 plus 2x minus 6 is equal to 0. So, 2x is equal to your 6 minus 2, 4, right? So, +4, so x is going to be equal to 2. But you know the maximum oxidation state is +6. So, it's certainly there is going to be SS bond. But it's a little different. See, you know H2SO4, isn't it? This is how your sulfuric acid used to look like. Now, of course, there has to be SS bond when we are talking about H2S2O3. The only difference is one of the oxygens is less. 2 hydrogens are there. It's just that one of the oxygens can be replaced here with sulfur, and to maintain the number of the covalency that sulfur maintains, which is 6, you have to put a double bond like this. So this is how H2S2O3 will look like. Now, OG, very important. P4O10, you already know that had 6 POP bonds, right? Check out P4O6. How is this going to look like? 4x minus 12 is equal to 0. So x is going to be equal to 12 by 4, 3. But maximum is +5. So calculated is less than maximum. So you will make PP bonds like this. Now, doubly bonded oxygens. If you're falling short of the oxygens, we can make POP bonds like this. So this is how you might draw. But mind you, please be careful. It's a 4-membered ring that you're drawing, my dear. It's a 4-membered ring that you're drawing. Lot of steric hindrance, lot of ring strain. There's a huge ring strain. You're making the phosphorus suffer. So when in trouble, take loan. Take loan from the bank when you're having trouble, when you're having financial strain. Here there is ring strain. So ring strain, because of that, POP bonds are going to exist, just like how you saw in P4O10, like this. So how many oxygens are done? 4 are done. 2 are left. This is how the other 2 is going to look like. And put lone pairs on phosphorus like this, and you're sorted. You're done for the day. So be mindful when you have P4O6. That's where the limitation of the trick is. So trick is wonderful, works well for JEE mains, JEE advanced, NEET examination very well. There can be exceptions, but if there are exceptions, please drop them in the comments and we can discuss them, right? Also try your NCERT 3 examples which are there for the paradox of oxidation state. You tell me what are those paradox of oxidation state 3 examples that I want you guys to write. And please now do not rant like Mayur, okay? Make inorganic chemistry your exceptionally strong subject. The exceptions should be your exceptionally strong companions.
सब्जेक्ट नहीं है, सब्जेक्टिव है. क्या कुछ नहीं किया है इस सब्जेक्ट के लिए. असाइनमेंट्स, नोट्स, फ्लैश कार्ड, आगे बैठा, 3 टीचर्स बदल दिए, पढ़ने की स्ट्रेटजी बदल दी, पर एंड रिजल्ट क्या?